Hello everyone, my name is Shitaye Megerssa. I'm from Ethiopia. I really feel honored to present our work on the DGRI, and I would like to thank the organizers for giving me this opportunity. And I will present the part of my PhD work, and the title of my presentation is Clinical Mapping of Seedling and Field Status Standards in DAKIYE Reichenbachii Durum population. As we all know, Durum is a tetraploid wheat species used for the processing of pasta and other food recipes that are consumed in different parts of the world. These end-use products demand both granular and quality, and these traits and other agronomically important traits were affected by several factors. And among those, stem rust of wheat caused by the fungus Vaccinia graminis, forming a special threat the most devastating disease, of course, common and Durum. This pathogen causes a completely loss and severe epidemics when susceptible varieties are grown. It causes assimilation from the plant system and cause harvesting of sugar seeds that downgrade the kernel and reduce product quality. The commonly used stem rust control methods are genetic resistance and application of fungicide. And the presence of genetic variability, genetic resistance is the most preferred because of environmental safety and cost efficiency. However, in case of no genetic variability available, fungicide application can be the only alternative to control this disease. Reichenbachii is a landrace among the collection of Pablo that was conserved in the US plant germplasm system. And this, the resistance in, so the older PGTOS around the world, in this variety was reported by Bacciore in 1991. So characterization and identification of loci and molecular markers linked to resistance in this population is of paramount for efficient transfer of resistance in the breeding germplasm pool, and also may introduce new sources of resistance to the germplasm pool. Therefore, the objective of this study was to evaluate a real population from DAKIYE Reichenbachii cross developed by the semi-bromide breeding program for seedling response to race jar CTUC and TTRTF, for field response to the bulk of race currently prevalent in Ethiopia and Kenya, and do linkage analysis and map those associated with seedling resistance and field resistance to multiple PGT race. So seedling evaluation was done in Debrezait in the greenhouse. And we used 224 F9 recombinant and breed line population. This were planted in pots filled with media, and we planted 3 seeds per pot in 2 replications. Then 7 days old seedlings were inoculated with spore suspensions based on the protocol developed by Rouse et al. And this table indicates the race and the isolates. And the isolates for JARS QC were from Plumsa, Ambo, and Barda, and those from TTRTF was from Georgia, Plumsa, and Debrezait. And we scored the seedlings 14 days post-inoculation using the 0 to 4 scale of stack movement, and we linearized these to a 0 to 4 scale to make it suitable for analysis. Field phenotyping was done in Kenya and in Ethiopia from 2019 to 2020. And we used the same breed population, randomized in complete flow design in 2 replications, and we repeated 3 checks after every 100 plots. Then we named them nursery based on the country name, the season, and the year. For example, ETOS 19 stands for Ethiopia of season 19. KNMS 20 stands for Kenya, main season 20. So we did inoculation using syringe at the stage of stem elongation on the spreader rows, and we first prepared the spore suspension. And then we did scoring using the modified Cops scale, and genotyping was done in North Carolina using the GBS protocol developed by Poland. This picture indicates the one on the left indicates the inoculation of spreader rows of spore suspensions at the stage of stem elongation, and the right one indicates the severity and response, the manual developed by CMIT, and severity by estimating the percentage of stem area covered with posture, and response as R, that stands for resistant, MR for moderate resistant, MS for moderate and susceptible, and S for susceptible. And those numbers below this response class were the numbers used, scales used to multiply with the severity to calculate the coefficient of infections that we use for further statistical analysis. And we used the last scoring for data analysis, and we did scoring 2 to 3 times. Phenotypic data analysis was done using the R statistical software by fitting linear mixed model. And if you see this table, the first column indicates the trial, the seedling test for the 2 races, and the field test for Kenya and Ethiopia. And the second column indicates the response. For seedling test, we use the linearized scale. For field tests, we use the coefficient of infection that was calculated from the last scoring. And in case of the Ethiopia main season 19, we transformed the data to square root because of skewed distribution. And we did this to meet the assumption of normality for linear model. So the 3 of their models look the same because we considered the genotype and the rep as random effect. The second column for the second row, we added the row effect as in the model because the fixed effect of the row was significant. In all these 4 cases, we use the LMR function of R, but for the second case, we used a linear function of R. From this linear mixed model, we estimated the variance components and calculated the heritability, and also the labs for the field response to use it in the QTL analysis. We did marker filtering and QTL analysis, and filtering was done before imputation, and SNPs above 20% missing data and about 10% heterozygous, and perfect LED removed from the data. And our QTL package for QTL analysis requires the ABH format. The A that stands for the homozygous allele for the susceptible parent, B for the homozygous for the resistant, and H for the heterozygous. For this, we use 7,418 SNPs for 201 lines, and we generated 929 SNPs for 119 lines that were polymorphic. And the missing data was imputed using the field genome function in the RQTL package. Then we further proceed with filtering. Then lines above 95% identical alleles with segregation distortion after pi-square test, and genotyping error, switched alleles, markers with double crossover counts above 10, and lines with crossover counts above 60 were removed from the data based on the manual prepared by Proman 2003. Then we did genetic participation estimation using the ensemble mapping function, and QTL analysis was done using composite interval mapping using 843 quality markers for 175 lines. And these graphs indicate the distribution of the coefficient of infection in the field, and for the linearized scale for the seedling response of the recombinant inbreed lines. And this slide looks a little bit busy. As we see here, the distribution in ET of season 19 was normal, and the one in ET MS19, the main season 19 was skewed to the resistance score, and in Kenya main season 19 was normal, and in Kenya main season 20 it looks bimodal. This difference in the distribution may indicate variation in race composition across the different environments and seasons. And we also estimated the heritability that ranged from 0.58 ET main season 19 to 0.85 in Kenya main season 19. And the one in Kenya means for some it was high heritability, indicating that this resistance was qualitative. And for the seedling test, the distribution in either cases was skewed to the susceptible score, and the estimated heritability was 0.76 for response to JARS QC and 0.80 for response to TTRTF. And these R's and S were the position of the resistant and susceptible parents in the response for the field and seedling. We also estimated the percentage of resistant, susceptible, and transgressive segregants of the rails across the 4 testing environments and the 2 races. As we see here, In Ethiopia, off-season 19 had higher percentage of susceptible land than Kenya in 2020 and 2019 and 2020. This indicates that the race in Ethiopia composed of more violent races through the Durum. This because of the GRCQZ race. The GRCQZ race was more predominant in Ethiopia than in Kenya. And we found about 16% transgressive segregants in this population in Kenya means 19, and it's good source of instance. We can see, we have to see if this instance was an old stage or an advanced stage. And for the percentage of resistance lines for race GRCQZ was a little bit higher than race TTRTA, indicating that the TTRTA is more violent than GRCQZ race, which was a recent race and caused epidemics in Italy. This graph is the heat map of recombination fraction in load score after filtering based on different filtering criteria, which is clear. We don't have any yellow strip on the blue background. Yeah, we removed about 5 misaligned markers and 20 lines with 95% identical names and 47 markers, genotypes with significant distortion, and 3 lines with crossover counts above 60 and 21 lines with double crossover counts to apply the data, and we came up with this recombination fraction in load score heat map, and we are good to go for the genetic map. So this graph indicates the distribution of the 843 quality markers and that are grouped into 13 linkage groups. And accordingly, the 843 markers covered 1,458. 10 organoids of the genome with an average interval of, excuse me, 1.73 cm. So the largest marker coverage was on chromosome 3B, followed by 7B, and also reasonable amount of markers were on 5B, 1B, 2A, and 3A. The others had low marker density, and we removed all the markers on 7A because of the low quality. And the genetic map indicated here was developed. Then using the composite interval mapping, we identified 3 QTL at a low threshold of 2.5. And the QTL was chromosome 3B was identified in 2 of the environments. In Ethiopia means the 19, Kenya means the 19. And also for the 2 races at the seedling stage. This indicates that this was representing an all-state resistance gene and contributed the highest to the phenotyping variance as we see on this aspect. So then the percentage of phenotypic variance contributed by the QTL was highest for the QTL on chromosome 7 next to that of the 3B. So this graph indicates the load score curve of the selected chromosomes, and the one on 3B looks high effect, large effect QTL, and the one on 4B is on the threshold, it's small effect QTL, and the 7B is also small effect. And as we see here, the 5A, there was a suboptimal QTL for the field response. And for the seedling response, we see here the 3B QTL had a little bit larger effect for response to GRCQZ than the TTRTA. And this graph indicates the QTL effect on disease reduction, and it looks higher for the GRCQZ than the TTRTA, but the reduction in disease responses was not much high. This was the QTL effect on disease reduction, which was larger for race in Kenya than race in Ethiopia. As you see here, in Kenya, the disease response was reduced from about 12 to -4, and from 12 to about -10. And in Ethiopia, it was from about 5 to 0, 5 to 0. So the QTL on 3B matched the QTL reported by batch gain, and the QTL on 4B was close to a QTL reported by the same author, identified for race in Minnesota, and the 7B is close to the SR17 reported by Latam. In conclusion, in the current population, the number of resistant lines to race GRCQC are more than that of PTRTF as a seedling stage. In the field, the proportion of susceptible lines are more to race in Kenya than race in Ethiopia. The proportion of susceptible lines are more to race in Ethiopia than race in Kenya. 7 lines that were consistently resistant in all testing environments carry 2 to 3 of the resistant alleles at identifying loci, and this can be used as paradigms in crossing and are needed to be evaluated for further evaluation. The 3 QTLs are previously reported and contributed by the resistant and Reichenbachii. The QTL effect on the response was generally small when we see it here, so we may need to do a single place test to see the actual effect on the response. The limitation of this study with the power to identify additional QTL in this real population will be limited by abnormal segregation, resulting in the removal of many low quality markers, and genome structural rearrangements of land progression can cause abnormal segregation, and cytological investigation will be required to resolve this question because this land race was an old collection and it may undergo some chromosomal rearrangements. And in conclusion, thank you for listening to me. And at last, I would like to thank the special committee, my special committee, Mark Sorrells, Gary Balstone, and Marcel Sasipiedo, the DGGW project for supporting my study, and Dr. Karim for providing my the study population and other team colleagues for helping me in various ways, and all the Sorrells lab, EIR, my home institute, and Gina Brown's lab, and my family. Thank you all for listening. I would like to take questions if you have some.